Our focus in this video is going to be on dividing polynomials. And just like we did with the polynomial multiplication section, we're going to be focusing again on the area model because it makes that connection with multiplication and division and helps organize the information for us. So this video is really broken down into three parts. The first part is going to be what we call dividing by a monomial. The term in the denominator, 3x squared, 2x, 7x squared, and 4x squared, is just a single term. Doesn't have 2, doesn't have 3, just one term we're dividing through. Now to do this actually is pretty straightforward. Essentially all we're going to do is we're going to take each of the terms in the numerator and put it over the denominator. Like so. And simplify where we possibly can. And then whatever we have left will be our answer to the problem. Now notice we took a polynomial and we're dividing by a polynomial. Sometimes we will still get a polynomial and other times we won't. But when I simplify that, 6 divided by 3 would give me 2. And then the x to the 5th and the x squared. There's 5 x's up here, 2 up there, or 2 down there. So in the end result, when I cancel them out, I'll have a 3 left over. So it's 2x to the 3rd for that first term. Similarly, our second term is going to be 4x squared. And our last term, the x squared cancels, but the fraction does not. And I'm going to be left with 4 over 3. So there's really no other simplification I can do. That's my final answer. If we look at a problem like the one down in the lower right here, a little bit more space that we're going to need to take up because we've got 1, 2, 3, 4, 5 terms, but our process is really no different. Actually, you know what? Yeah. Nah, I'm sorry. Let's go with this one in the lower left because there's some really cool stuff that's going to happen here. We have 14x to the 7th, which we're going to divide by 7x squared. We've got negative 28x to the 5th, which we're going to divide by 7x squared. We've got 13x to the 3rd, which we're going to divide by, you guessed it, 7x squared. And finally 7x, which divide by 7x squared again. So each term divided by that denominator. We will simplify. And so when I simplify this, I'm going to take 14 divided by 7, that's 2. And the x's become x to the 5th. Here I've got 28 over 7, that's going to give me a 4. And that's x to the 3rd. And this is where things get a little bit dicey. 13 over 7 does not reduce, so I can write that like that. And x to the 3rd over x squared, there's still one x left in the numerator. And I'm going to put that up in the numerator just because I think it helps keep track of the information a little bit better. Technically, you could also write it as 13/7 x. But what we can't do is put the x in the denominator. Then we do the same thing with the 7x. The 7's will cancel, so that turns into a 1. But we have an x squared in the denominator and x in the numerator. So that tells me that I'm still going to have an x left in the denominator. So what happens in this one is once we fully simplified it, we ended up getting an x in the denominator, which no longer makes this a polynomial for our resultant division. Not a big deal, but something to consider that you're not always going to get polynomial answers when you divide. That 1 was considered a remainder, and you'll see that later when we do the full-blown division. Okay, so with that in mind, let's do a problem with the area model. So we're starting with a quartic polynomial, x to the 4th plus 3x to the 3rd minus x squared minus x plus 6, and we're dividing it by x plus 3. Here's where things get a little bit strange. When we're using the area model to divide, essentially this part right here, the x to the 4th, that numerator, is what would fill all of this stuff in here. So it's not the top row, it's all this stuff here that I'm trying to fill out. There's one piece I know. I know x plus 3 is one of the polynomials that I would use to multiply to give me this product. That's what I'm trying to do. I'm trying to work backwards from my answer to figure out what the two pieces multiplied were, knowing one of them. So to start this off, I'm going to take that denominator x plus 3 and I'm going to put this in the first column. And that's going to kind of be my starting point. I know that my highest degree term is x to the 4th, not only because it's listed first, but because it's got the highest exponent. based on the structure of the area model, that term has got to go here. So that term has got to be an x to the fourth. So this is where it gets interesting, because I'm trying to basically follow a pattern and put pieces in place where they need to go. And instead of just taking things and plugging into the area model and going through the multiplication, I'm actually working backwards and trying to figure out what those pieces would have been. So I have x. I ended with x to the fourth. That means that this term right here would have to be an x to the third. It's the only way to get x to the fourth, by starting with x. X times x to the third is x to the fourth. Well, based on that, I know that right here I should have a 3x to the third. So I'm completing the area model. Wait, our diagonals are like terms. So x to the third, I want to have these two things add up to equal what's in the numerator here. So if I take 3x to the third plus something, and I get 3x to the third, what we actually are going to have for that something is a 0. It's 3x to the third plus 0x to the third gives me 3x to the third. Okay, based on that, x times something gives me 0x to the third. That must have been 0x squared, which would then make this 0x squared when I multiply through. And again, my like terms are on the diagonal. So together, these two x squared terms have to give me a negative 1. So let's fill it out. That's got to be negative 1x squared, which then means that to get from here to here, I had to make this a negative 1x. And you can just write that as negative x. It's the same idea. That makes this a negative 3x. And once again, I'm looking for my diagonal. Those two terms together have to add up to negative 1. Since I already have a negative 3, I'm going to have to add to that 2x. And if that's a 2x, then that must have been a 2. 2 times 3 gives me 6. So what I have left then is a 6, which is exactly what I have in my numerator. So things worked out really well for me. I don't have a remainder. I don't have a leftover. So the big question then is, what the heck is the answer? So again, this is all of this together gives me that numerator. This is what I divided by. My end result is that. X to the third. I don't need to write the 0x squared, so I'm not going to. Minus x plus 2. Let's look at another one where things are going to change a little bit, but our process is still going to be the same. The first thing I want to do then is I'm taking this cubic term, or polynomial I should say, and dividing it by a binomial, 3x minus 2. That first box I'm going to fill out with 27x to the third. So now what I'm looking to do is figure out what goes here. 3x times what gives me 27x to the third? Well, 9x squared. And so that would give me negative 18x squared. Again, along my diagonal are my like terms. I have negative 18, and I want to turn into a positive 9. So to that, I have to add 27x squared. If that's a 27x squared and I started with a 3x, that must be a 9x. So this is negative 18x. My x's have to add up to negative 3. So I had a negative 18. I want to make it negative 3. That must be 15x. Well, that's a 5. And that would be a negative 10. But that doesn't match what I have in my numerator. I've got a negative 9 in my numerator. So what I actually need to do is add in another column to make it a little adjustment. So my adjustment is I'm going to take a negative 10 and turn it into a negative 9. That means I'm going to have to add a 1. That 1 represents a remainder. So here's how we're going to write that. We're going to take our final answer which is the division part of it, 9x squared plus 9x plus 5. And to that, we're going to add our remainder divided by our original divisor, 3x minus 2. It's a leftover that we have to account for. We still are dividing it by that 3x minus 2. And so there's our answer. Again, remainder over your original divisor gives you your final piece. All right, last thing we're going to talk about, we're going to make this fairly quick. All right, so here we've already completed some divisions. X to the third plus 3x squared minus 14x plus 8 divided by x minus 2 gives us that quantity there, and so on. In 3 of these, we end up having a remainder. What we're asking it to do is take f of x, which we're defining as our numerator, x to the third plus 3x squared minus 14x plus 8. And we're going to compute f of 2. Now, f of 2 has a relationship with that denominator. F of negative 6 has a relationship with the denominator. F of 5 has a relationship with the denominator. So what they're asking us to do is to take this expression here, f of 2, and evaluate it. So when I evaluate f of 2, and I'm going to save you the gory details of this, but essentially when I find f of 2, what I'll end up getting is 0. This is asking me to find f of negative 6, so I'm going to plug that into here. And again, kind of the behind-the-scenes stuff, we end up getting 9. F of 5, we do the same thing. F of 5, we get negative 3. And if I did that here, f of 5, I got 1. So you might be saying, wait a minute, there's some kind of relationship here. So you're not going to see it in this first one, but in the second, third, and fourth, it might show up a little bit easier. When we have that f of negative 6, so again, that negative 6 was the opposite of that expression. So essentially, we took it and set it equal to 0. When I evaluated that, I got this number right here, which just so happens to represent my remainder. And same thing here. When I took x minus 5, set it equal to 0, so that's 5, and evaluated in the numerator, that was my remainder. And when I took the same thing over here and evaluated 5, I got 1, which just so happened to be my remainder. So that's a cool thing that happens with polynomial divisions. You can easily find out the remainder and see if it works out really well. Cool thing is, too, if you have a remainder of 0, that means the quantity goes in completely, and it's factorable. So x minus 2 in the top one up here would have been a factor of x to the third plus 3x squared minus 14x plus 8.